Imagine a group of children sharing a single swing in a playground. Before a child steps onto the swing, they look to see if anyone else is already swinging. If the swing is free, they jump on; if not, they wait. This simple look before you use rule is the idea behind Carrier Sense Multiple Access, CSMA. In a computer network, many devices, computers, phones, printers, share one wire or radio channel. They must first sense the carrier, that is, listen to the channel, to see if another device is already talking. If the channel is idle, they start to transmit. Without this rule, devices would start talking at the same time, causing a mess called a collision. Therefore, CSMA is necessary to keep the shared medium orderly, just like children watching the swing keeps everyone safe and the playground fun. When two children try to swing at the same time, they bump into each other, and both fall off. That is a collision. In Ethernet, using CSMA with collision detection CD, each device not only listens before sending, it also keeps listening while it is sending. If it hears a signal that does not match its own, it knows a collision happened. The system must guarantee that a device can detect a collision, even if the other device started a little later. Let tau be the one-way propagation delay. The worst case is when device A starts at time 0, device B starts just after A finishes sensing the medium, and is located at the far end of the cable. B's signal reaches A after 2 tau. To be sure it can see B's signal, while it is still transmitting, the transmission must last at least 2 tau. Ethernet defines a slot time equal to 2 tau. The frame must be longer than 1 slot time. Mathematically, the minimum frame size L sub min in bits is L sub min equals R times 2 tau, where R is the link data rate. For classic 10 megabits per second Ethernet, with a maximum cable length of 2,500 micrometers, tau approximately 25 microseconds, so 2 tau approximately 50 microseconds, and L sub min equals 10 times 10 to the 6 times 50 times 10 to the minus 6 equals 512 bits, equals 64 bytes. This is why Ethernet frames must be at least 64 bytes long. It guarantees every device can notice a collision. After a collision, the devices do not just try again immediately, they wait for a random period. This is the binary exponential backoff algorithm. The idea is similar to two kids who drop their toys after bumping. They wait a random number of seconds before trying again, so they are less likely to bump again. When the first collision occurs, each device picks a random integer k from the set 0 to 1 and waits k slot time before retransmitting. If a second collision occurs, the range doubles 0, 1, 2, 3. After the ith collision, the range is 0 to 2 to the I-1, but it never exceeds a maximum of 2 to the 10, which is 1024 slots. The expected backoff time after I collisions is E of t backoff of I equals open parenthesis 2 to the I-1 close parenthesis divided by 2 times slot time. The probability that a device will retry in a particular slot after I collisions is 1 over 2 to the I. As the number of collisions grows, the chance that two devices pick the same slot becomes very small, reducing repeated collisions. The expected total delay until a successful transmission can be summed over the distribution of collision counts. But the key insight is that the backoff grows exponentially, spreading retries over a larger time window and thus lowering the chance of another crash. The throughput of CSMACD is the fraction of the channel's capacity that is used for successful frames. Let G be the average number of transmission attempts, including retries generated per packet time, and let rho equals G times T subframe divided by T subslot be the normalized traffic load. The probability that a slot is idle is P idle equals E to the minus G. A transmission succeeds only if exactly one device starts in a slot, which occurs with probability P suck equals G E to the minus G. Therefore, the efficiency S, successful frames per slot, is S equals G E to the minus G. The throughput bits per second is then S times R, where R is the link rate. This formula shows a bell-shaped curve. As traffic load rho increases from 0, throughput rises, reaches a maximum at G equals 1, where S equals 1 over E. Approximately 0.37 of the slots carry successful frames, and then falls because collisions dominate. In practice, Ethernet networks are designed to keep ρ well below 0.1 to 0.2, yielding efficiencies above 80% when the average frame length is much larger than the slot time, the large packet effect. In wireless networks, the medium is shared through the air, and devices cannot always hear each other, hidden node problem. Imagine a garden where Alice talks to Bob across a hedge. Charlie standing behind the hedge cannot hear Alice but can hear Bob. If Alice talks to Bob while Charlie talks to Bob at the same time, Bob receives two overlapping voices, a collision. IEEE 802.11 uses RTS/CTS, request to send/clear to send, to avoid this. Before sending a big data frame, a device first sends a short RTS packet. All devices that hear the RTS, including hidden nodes, set a timer for the upcoming transmission. The intended receiver replies with a CTS packet, which can be heard by devices that missed the RTS. Once a device hears either RTS or CTS, it knows the channel will be busy for the duration announced in those packets and therefore refrains from transmitting. This reservation mechanism protects the medium from hidden node collisions, much like a traffic officer waving a flag to tell everyone to wait while a car passes a narrow bridge. Even with RTS/CTS, Wi-Fi devices still need a rule for when to try sending their RTS. This is done with a contention window, CW, a range of slot numbers from 0 to CW-1. After the channel is sensed idle for a short DIFS interval, a device picks a random backoff counter K in that range and counts down one slot each time the medium stays idle. When the counter reaches 0, the device transmits. The size of the CW changes similar to binary exponential backoff. After each failed attempt it doubles, CW becomes 2 times CW plus 1, up to a maximum CW max. This makes the probability of two devices picking the same slot equal to 1 divided by CW. For example, with CW equals 16, the chance of a collision in a given slot is roughly 1 divided by 16. By randomizing the slot choice, devices spread their attempts over time, reducing the probability that many devices collide at once, just like children drawing lots to decide who gets to use the swing next. Explanation: how well CSMA performs depends on two big factors: propagation delay, how long it takes a signal to travel across the medium, and network load, how many devices want to talk. Low propagation delay, light load, picture a short hallway with few kids. When a child starts talking, everyone hears it almost instantly and collisions are rare. CSMA/CD works almost perfectly. Efficiency can be above 95%. High propagation delay, heavy load, imagine a long corridor where it takes time for a shout to reach the other end and many kids are shouting. One child may start speaking, but another far away may not hear it yet and start at the same time, causing a collision that cannot be detected quickly. The slot time must be long, limiting how many slots fit in a second, and many attempts become collisions. Efficiency drops sharply. Ethernet with very long cables greater than 2 kilometers would need larger minimum frames, otherwise throughput collapses. In wireless, propagation delay is tiny, the speed of light, but the air is shared and hidden nodes increase effective load. CSMA/CA with RTS/CTS mitigates collisions, but as the number of stations grows, the contention window must grow, and throughput falls roughly as 1 over square root of n, where n is the number of active stations. Hence, for dense Wi-Fi deployments, other methods, for example scheduling or multiple channels, are preferred. The slot time is the fundamental time unit for both CSMA/CD and CSMA/CA. It is chosen to be at least twice the maximum one-way propagation delay on the medium, ensuring a device can detect a collision within one slot. For classic 10 megabits per second Ethernet, slot time equals 512 bit times equals 51.2 microseconds, approximately 2 tau. Propagation delay tau depends on the physical medium. Copper cable approximately 5 nanoseconds per meter, fiber approximately 5 nanoseconds per meter, or radio approximately 0 nanoseconds for short distances. Longer media leads to larger tau, which leads to larger slot time, which leads to larger minimum frame size. Media type also influences whether we use collision detection or collision avoidance. Wired media can listen while transmitting, so they can detect collisions, collision detection. Radio cannot reliably listen while transmitting because the transmitter drowns its own receiver, so wireless uses collision avoidance. It avoids the collision before it happens instead of detecting it afterward. These physical constraints shape the protocol parameters, just as the size of a playground and how far children can see determines how they decide when to use the swing.